turn it on the microphone. So many students ask me a question about this product of Lewis with the symbol with the summing over from 1 to 3. It's actually delta IP delta JQ minus delta IQ delta JP. So here delta IJ is 1, 0 when I equal J, when I is not equal to J. So it has a name called Kronecker delta. So this delta, this is a symbol, is called Kronecker delta. And this delta ij means when I and j are the same, it is equal to 1. And when I and j are different, then it is 0. And I have done this explanation carefully in last week, so I don't think I need to do it again. But the importance of this relationship is you can actually simplify this vector product. B, C, A minus C, A, B. And actually, I have shown that you can obtain the same result that just multiplying 3 vectors using brutal force. So here A, B, C are vectors. And vectors can be constant or function of many things. So when the vector, say f, is a function of space-time, that means x, y, z, t, or sometimes just a space, or space, x, y, z, we call f a vector field. So when we say vector as a vector field, then it's a vector, but it also depending on the position and the time, or sometimes the position. And normal function f x y z or f x y z t is called scalar field. So just so it's a notation, so I just want you to be familiar with the I think I need to move this a bit too low, so Okay, thank you. Right. Yeah, this is much better. So it's just simply a notation. So scalar field, vector field. This is new notation. So it's a function. Or function. Or vector with dependence on x, y, z or x, y, z, t. So sometimes if you can represent this way, x, y, z, t is component-wise x, y, z, t, x, fy, x, y, z, t, y, f, z, x, y, z, t, z. So this is when f is not dependent, depending on x, y, z, t. Or when the vector field is not depending on t, then we can just represent x, y, z. So, or we have a different vector field, which is only a function of x, y, z. Then we can also represent gx, x, y, z, x, gy, x, y, z, y, and gz, x, y, z, z. And I guess so far, so good, right? Very special vector is called position vector. So assuming that we have some curve, and we have a reference point, your reference, and we can define some position. This is P, X, T, Y, T, Z, T. So in this case, T is a parameter, and this we can define the distance as ST. At some point, a different point, Q, X, T plus delta T, Y, T plus delta T, Z plus T, delta T. So this is R plus delta R, and this is called delta R. Just a moment. 잠깐 전화가 와가지고. Okay, sorry about that. So I had to answer some phones. Okay. So let's say ST is a distance along the curve. So to change so ds tr is actually ds dsx plus ds dyy ds dzz. So let's say this is a ds. So actually ds square is same as change over dx square plus dy square plus dz square. So that's the distance between two PQ. ds distance between P and Q. So X is actually changed by ds. So maybe I should use this delta R. Your distance is ds. So ds is actually delta R, delta R. Delta R is delta x, x, delta y, y, delta z, z is actually same as ds. I should say this one. So delta x is actually ds dx ds. So from this we can have very simple relations. ds dr is equal to 1, right? This is actually dsx, dx, dyy, dzz. So ds dr is same as ds dr dot ds dr is ds dx square ds dy square ds dz square same as 1 over ds dx square dy square dz square. But this is same as ds, right? So along this curve, actually, ds dr is a tangent. So this is actually ds dr is a unit tangent to the curve C. It's probably you have studied this material when you're a freshman in your calculus class, right? Or how should I say? The basic physics classes. So we found that the ds there is sorry. There's a curve, C. It's parameterized by some parameter T. And we have some reference point, O. This is your position vector, RT. And this is ds. So ds is a length along this curve. Then this is delta ts, dr, ds, dr. ds, dr is a unit tangent vector to the curve C. So this is a ds. Then we are interested in the change of function f x, y, z. Let's say, think about this x, y, z along this curve. So this is P, this is Q. So this is R plus delta R. This is delta R. So P, the point P is x, y, z. And Q is x plus delta x, y plus delta y, z plus delta z. So we are interested in how the function changes along these 2 points, along this curve. So fq minus fp, this is a change of function of a function f along the curve C from a point P to a point Q, right? So this is simply f x plus delta x, y plus delta y, z plus delta z, minus f x, y, z. And in the spring semester, I told you about the philosophy of doing nothing. Anybody remembers what doing nothing? No? So, when things got complicated, do nothing. So this is a really important statement in my class. So when you encounter very complicated problems or complex problems, or you don't know how to do that, then just simply do nothing. But do nothing mathematically. So there are 2 ways of doing nothing in mathematics. So doing nothing in mathematics. So my handwriting is still difficult to recognize, I guess. So you will get to use it when, by the time of the first quiz. So number 1, add 0. That's one way of doing nothing, right? Another is multiply by 1. That's another way of doing nothing, right? So let's take a look at this function, fp fq minus fp, which was fx plus delta x, y plus delta y, z plus delta z, minus f x, y, z, and you don't know what to do. So let's apply the philosophy of doing nothing. And in this case, we can add 3 zeros. So how do you make 0? You can subtract something and add the same thing, right? That's basically 0. So I would say f x plus delta x, y plus delta y, z plus delta z. I like to subtract one thing, x, y plus delta y, z plus delta z. I subtracted this, so I added here, same thing, right? So this part is the same as this, right? So fx plus delta x, y plus delta y, z plus delta z is same as this original function, and then I subtract fx, y plus delta y, z plus delta z, plus the same thing. So it's basically 0, right? And another 0, I subtract this, x, y, z plus delta z, plus f, x, y, z plus delta z, minus f, x, y, z. So I added another 0, right? So this is actually 0, and this is another 0. So I added 2 zeros, and I didn't make any changes, right? So let's move to the next page. Luckily, I remember the older formula, so I just copied again, and some of you still need time to copy, or so. Let's just simply just write it once more. So I keep forgetting to change the color. So f x plus delta x, y plus delta y, z plus delta z, minus f x, y, z is same as f x plus delta x, y plus delta y, z plus delta z, minus f x, y plus delta y, z plus delta z, plus, we need some space between the next line, f x, y plus delta y, z plus delta z, minus f x, y, z plus delta z, plus f x, y, z plus delta z, minus f x, y, z. Still, you don't know what to do. So now let's try to multiply by 1. So if you divide the whole thing by delta x and multiply by delta x, still same, right? Okay, I'll put some parentheses. Actually, brace. delta y, delta z, delta z. Something familiar for you? So y and z are the same, right? But only the x has been changed from x plus delta x to fx, and then you divide by delta x. So there's a change of function with respect to delta x, and this is the same as a change of function with respect to delta y, and this is a change of function with respect to delta z. So we can write down in this way: partial x, partial f, delta x, plus partial y, partial f, delta y, partial z, partial f, delta z. For small delta x, delta y, delta z. Then this can be written as the inner product between two vectors. Partial x, partial f, x, partial y, partial f, y, partial z, partial f, z, dot delta x, x, delta y, y, delta z, z. So this is actually delta r. We call this gradient of f. Called gradient of f. Am I going a little bit too fast, or it's about right? Okay. So gradient of f is defined as partial x, partial f, x, partial y, partial f, y, partial z, partial f, z, and you can write down this way too. Or x partial, y partial, z partial, f. You can write this way too, right? So we sometimes call del operator. So del operator is simply a vector differential operator and can be treated as a vector. Very interesting, right? So that operator, which is also a vector, it can be treated as a vector, and it has many interesting properties if you study differential geometry. But we just, for now, let's just accept this as a vector. It can be treated as a vector. So let's go back to the original. We have some curve. This P. This is Q. R. R plus delta R. This was delta R. So F Q minus Fp was actually gradient of F delta R. And delta R is actually unit tangent, right? It's tangent curve. So delta R is tangent vector. So maximum change so if you like to see the maximum change of F, then this gradient has to be parallel, right? So gradient for maximum change of F F delta R is parallel to the tangent vector over curve. See. So we will get back to this later, but let's for now just accept that if you like the maximum change of function along the curve, then the direction of the change is along the tangent or gradient. And without, worrying too much about the physical meaning, this der operator can be applied to other vectors. So say F is Fx F z x y z z. Then the first thing is you can make an inner product with del, with F. So anybody remembers? So this component we can regard this way. There is x del x, y del y, z del z. Here del x is partial x partial, del y is partial y partial, del z is partial partial z. So we can assume this is a vector component of this vector. Then this is simply del x fx plus del y fy plus del z fz, right? According to the definition of the inner product we studied last week. So this is basically then del f is partial x partial fx, partial y partial fy, partial z partial fz. And it has a name, it's called divergence of F. F. So for example, if F is given by the following function, can you calculate the divergence? Divergence of f is simply partial x, partial xy, partial y z, partial zx is simply, so what is the part, what do you get if you differentiate xy by x? Y, yz by y, z, zx by z, x. So this is y plus z plus x, right? Very simple. So divergence of vector is a scalar. And divergence of a position vector this is easy one, right? Partial x, partial y, partial z. So what do you get if you differentiate x by x? 1. Y by y, 1. C by z, 3. For scalar functions, say another example, x, y, z. So gradient f x, partial x, y, z, partial x, y, z, x, y, z, which is the first component y, z, right? Second component x, z. Final component x, y. Sometimes, many cases, we have r, which is x squared plus y squared plus z squared, which is r dot r. What is gradient of f? R? A bit complicated, right? X, partial r, y, partial r, z, partial r. Maybe you need some space here. Let's say partial x, partial r. Partial x, x squared plus y squared plus z squared. Anybody learn the chain rule in the spring semester, right? So we can put this whole thing as some g. Then you can chain rule dg d root g partial x partial g, right? This is a chain rule. Chain rule. CHAIN, oh, maybe. So this is 2 root 2g over 1. This is 2x. So this is root 2g is actually r over x. You probably have learned about this chain rule in freshman 미적분학 or calculus, right? Or actually, if you have taken my class, you have learned in my class in the spring semester too. So if you're not familiar with, then maybe you can go to my website and check the lecture note for the spring semester. Then you will find the chain rule part. Or so this is actually x r over x, y r over y, z r over z. It's the same as r over r vector. So this is an interesting part. So before I proceed, maybe you can take a break for maybe a few minutes. And 지난번에 이름 없는 사람 한 10명 있었는데 다 확인해봤어요? 주소부터 확인해봤어요. Okay. So let's take a break for a few minutes before we start again. And I'm here, so I will just briefly review chain rule. Simple approach. So let's just consider the following function f is a function of g through x. So change of function delta f is f gx plus delta minus f gx, right? So this change of function can be written as a gx plus delta g, correct? So I mean gx plus delta can be written as a gx plus delta g for small delta x. So when delta x is 0, then delta g is of course 0. So derivative is actually dx df is you apply delta x goes to 0, delta x delta f, right? That's a definition of the derivative. Delta x f gx plus delta x minus f gx. And delta g is actually gx plus delta minus gx, right? So it can be written as g plus delta g minus f g. I used to know how to make a copy and paste, but I forgot. So I'll just simply write it down unless it's okay. Is it this? No. I guess this is not. Okay. X or delta. Okay. I think it has to be delta, right? Or delta. delta. Small delta. Complicated. So, but let's try. I'll try to find out how to do that next time. So I have to write it again. So dx df plus delta x goes to 0. Delta was it? So over delta f 3x plus delta minus f 3x. That's the same as delta goes to 0. Delta f(g) plus delta g minus fg, right? Still, you don't know how to do that, what to do next. So what you can do is doing nothing. So multiply by 1. So I like to multiply by delta g and delta g. So this is basically 1, right? So I just multiply by 1. And also we know that when delta goes to 0, delta g also goes to 0, right? Delta goes to 0, delta g goes to 0. And we can change this order, delta g, f 3 plus delta g minus f g. And this is delta. And delta g is simply what? G x plus delta minus gx, right? Gx. So this is actually delta g. So it's nothing but, so we have tg df dx dg. This is the idea of chain rule, right? So when f gx through gx, then dx dg, df is, you first differentiate f by g, and then dx dg. When you have more than one variable, then the d become partial derivative. So we can generalize when f is f through g x y z. Then you can generalize. Partial x partial f is dg df partial x partial z, right? Partial y partial f is dg df partial y partial z, and partial z partial f dg df partial z partial g. This is generalization. So I think you have learned this in your freshman, right? But that's 6 months ago, or almost a year ago. So most of you might have forgotten. So maybe this is a good chance to recall your memory. And actually, you have to do in September 25 when we are going to have the first quiz. So that's a generalization. So any questions about chain rule? No. So you understand everything, right? So let's do some more example. Am I going too fast or still okay? My speed is okay? I'm loud enough? Good. So a more general case when, I like to use blue color. So for f is a function of r. R is x squared plus y squared z squared. So by now, you know this derivative, partial x partial r is r over x, right? Partial y partial r is r over y. Partial z partial r is r over z. So this is actually a good example for checking the chain rule. For the chain rule. So now what is the gradient of fr? So this is, according to the definition, partial x partial fr, y partial fr, z partial fr. And then you can apply the chain rule to each of the component. So partial x partial r become dr dfr, right? Partial x partial r, y dr dfr, partial x, y partial r, z dr dfr, partial z partial r. It looks like they are the common factors, right? So we can put them together as a common factor. And this is x, r over x, y, r over y, z, r over z. So this is actually dr df r over r. Sometimes we write r hat as r over r. This is a unit vector in r direction. So then we can write this way, r unit vector dr df. So gradient has a very interesting properties. So we can also form a vector product with the del operator. So can I move on? It's the time to copy. Yeah, somebody told me that actually my handwriting is really fast. Is it? I'm writing too fast? Or my voice, my talk is fast? Which one is faster? Handwriting or my talk? Handwriting is fast? Okay. So I'll try to slow down as much as possible, but sometimes I just got carried on, so. So del can be also used as a vector product. This is called call over f, or call f. called curl. Simple x partial y partial f z minus partial z partial f y plus y partial z partial f x minus partial x partial f z plus z partial x partial f y minus partial y partial f x, or curl f's I component is simply sum of j k epsilon I j k partial x j f k. So here x1 is x, x2 is y, x3 is z. Of course, 1 is x, 2 is y, 3 is z. So we can use a Levi-Civita symbol to simplify the representation of curl F, or you can just write down the component by component. 네. 유닛 벡터요? There is no unit vector. I mean, because curl is defined by the vector product. 벡터랑 일단 우리 아까 원래 지난 시간에 했던 그 A 플러스 B의 A를 제일 바꾸는 것 같았는데, I mean, okay, so for comparison, when you say A cross B, we learn this way, right? X component A y B z minus A z B y. That was the definition of for the, and y, that's a unit vector y. A z B x minus A x B z plus c A x p y minus A y p x, right? So we just replace this. For curl F, A is del operator, B is F vector, right? So AX is actually del X, AY is del Y, AZ is del Z, right? And PX is FX, PY is FY, PZ is FZ. So you just substitute A and B by del and F, and then you put this into this. Then A cross, no. Curl F is same as this. So this is a del Y F C minus del Z F Y, Y component, the unit vector in Y, del Z F X minus del X F Z plus z del x fy minus del y fx. So del x is simply partial, so we can say x partial y partial fz minus partial z partial fy plus y partial z partial fx minus partial x partial fz plus z component partial x partial fy minus partial y partial fx. So does that answer your question? Great. So maybe it's good to have some example to work out, right? So let's worry about the physical meaning of curl or divergence until later. So, and it's probably better just be familiar with how to calculate those quantities before. So, example. Okay, you'd like to choose any good example? Democracy. X. YZ, Y, ZX, Z, XY. So this your FX, FY, FC. So call F X component. Start with a big parenthesis. X, Y, right? Y, F, Z minus partial Z, partial F, Y. Let's start with this simple way. XZ, Fx minus X, Fz plus Z, partial X, partial Fy minus partial Y, partial Fx, X, partial Y. What is Fz? Xy, right? Partial Z, Fy was Zx, Y, partial Z, Fx was Yz, minus partial X, partial Fz, Xy. I have a very odd feeling that you are going to get 0 for this particular example. X, Y, so Zx, minus partial Y, partial Fx, Yz. Where shall I do? Maybe have some room here. So X. So what is partial Y, partial X? X. And what is partial Z, partial Zx? Well, I didn't intentionally do this. What is partial Z, partial Y, Z? Y. What is partial X, partial XY? Y. What is partial Z, partial Z, right? Minus, So for this particular example, it was a 0. But it's not always 0. So I don't want to misunderstand that the core f is always 0. So let's try to find out what is not. Maybe another example. What's the previous example? yz, zx, xy. Something familiar? This can be written as a gradient of x, y, z. Right? So gradient, the first x component of the gradient is partial x is y, z, right? So y, z, x. And second component, y component, actually, partial y, partial x, y, z is x, z. And this is x, y is partial z. So I have a hunch that curl of a gradient is 0. So we can double check. Okay, the random selection, why don't you supply the function? Any function. Some simple one, hopefully. No idea? YG? Y. Y square, okay. Y? Z square? Okay, let's see if this is not 0. Z? X square? Uh-oh. I have a very odd feeling that. Well, let's check. Okay, so this is your fx. This fy. This is your fz. So call f the x component, partial y, partial fz minus partial z, partial fy, right? Plus y, partial z, partial fx minus partial x, partial fz, plus z, partial x, partial fy minus partial y, partial fx. All right. So partial y, partial z. Uh-oh. Partial y, partial z. X, if you differentiate x squared by y, what do you get? 0. And fy, fy is z squared, right? And if you differentiate by z, great. Minus 2z is not 0. Oh, great. Okay, if you differentiate fx, so y squared by z, you get? If you differentiate y squared by z, what do you get? 0. Minus, partial x, partial fc. Oh, this is nice. X squared. If you differentiate by x, what do you get? 2x. That's a really good example. It's non-zero, right? Partial x, partial y. Fy is z squared. If you differentiate by x, you'd get 0 minus partial x, partial y by fx. So if you differentiate y squared by y, 2y. Nice job. Minus 2zx, whatever this function is, y, 2yz. So this is not 0 in general, right? Good job. So you can ask me a question. Why the previous example you get 0? And the second example is not 0. So there are some cases when, so you can pay a careful look. So question, y squared is square, x square. So x y square, y z square. This is good example, so maybe we can use this one. Same, right? Square. Previous result. This one, 2z, 2x, 2y. 2z, 2x, 2y. Oh, not the same. cxy. Curl of some gradient f is 0. You can check, right? So, curl of gradient of f is actually x component, partial y partial gradient f z minus partial z partial gradient f y plus y partial z partial gradient f x minus partial x partial gradient f z plus z partial x partial gradient f y minus partial y partial gradient f x. And so it turns out that this, so partial y partial, what is the z component of gradient f? This is partial z partial f, right? And this is partial z partial y partial f plus y partial z partial x partial f minus partial x partial z partial f plus c partial x partial y partial f minus partial y partial x partial f. So actually when you differentiate, you can change the order, right? So there's some more space. The same as x partial y partial z partial square f minus, and if you differentiate second order derivative, you can change the order of the derivative. So same as this, partial y partial z partial z partial x. So this is 0. So we found that the curl of a gradient is 0. But actually you can also regard this with a very simple notion that this is a cross a f. So the vector cross with the same vector is always 0, right? The angle is sine 0. This is also 0. So you can regard this way too. Make sure that sorry, what happened? Oh my goodness. Go back. I want to delete this page, and well, let's just have a blank page. We can also form apply call twice. Very exciting, isn't it? So remember the formula that A cross B cross C was B AC C AB, right? So this is A, this is B, this is C. So call F is actually call over F. So actually it has to, C has to come this way. Minus because their operators become before the function. And this particular operator is called del square, which is partial x square, partial y square, partial z square, partial is called the Laplacian. So let's calculate this for non-zero f. So maybe you can use the same example that we used before. That say f example. F x y square, y z square, z x square. Let me see. Interesting thing is the divergence of f is very interesting. In this case, what is divergence? Partial x, partial fx, partial y, partial fy, partial z, partial fz is equal to 0. So, in this case, we have a very simple formula. Minus Laplacian square f is partial x square, partial y square, partial z square, partial square, and we have x y square, y z square plus z x square. In this particular Cartesian coordinate, the differentiation doesn't affect the unit vectors. So we have minus, the first component is this, right? Everything is 0 when you apply this, only this. So x 2y, and this one minus y 2z minus c 2x. Very interesting. And this result is familiar. If you apply call twice, same as the result with the call. 2i, 2z, 2x. Familiar? I created the page. How do I delete the page? Is there any way that I can do this? Sorry. So actually it's not same as call. It's something different. And possible application is the following. So 18th to 19th century by James Clerk Maxwell. So the electromagnetic, how many of you are taking 전자장? Some of you, maybe, actually quite a number of you are taking this 전자장. So 1870 something, the James Clerk Maxwell actually formulated the electromagnetic theory. So the electricity and magnetism has been known for a long time, since the magnet, maybe 2,000 years, but it was Maxwell who formulated mathematically. So electric field magnetic flux density. So electric field and magnetic field are the two basic ingredients in H, magnetic field. And HT, electric flux density. Electric flux density. J and B mu H. This is called permeability. 투자율 and permittivity. This is called permittivity. 투자율. I don't know how to call this permittivity in Korean. So nu and epsilon are actually properties of a material. So epsilon and mu are the basic properties of a material. So this is called Maxwell's equation. So electricity and magnetism has been known for almost 2,000 years, or maybe even before that, through the history of time. But it was Maxwell who was able to formulate the electromagnetic phenomena in terms of mathematics. I mean, gravity was known for a long time, but it was Isaac Newton who formulated it mathematically. So until the end of the 19th century, we thought that there are two basic forces in nature. One is gravity, The other one is electricity and magnetism. So these two are the basic building blocks of nature. Of course, there are two more discovered much later. But until then, so comparison, there's Newton's law, right? 17th century. So this is actually a very important equation, first one. This is another name is Faraday's law. That next week we will learn this Faraday's law more explicitly. But Faraday's law actually says how to generate electricity. Electricity. This is really important. So Faraday's law, which is basically something like that. If you have a closed circuit, and if you have a moving magnet inside and outside, it produces electricity. Probably you have learned that, right, in high school. But mathematically, the Faraday's law is same as this. The time change of magnetic field is same as curl E. It's a Faraday's law. And this is, I don't know what. And Maxwell, actually, was very good at mathematics. So he tried to F sorry. This is very interesting from historical perspective. So Newton's law. And with calculus. It was 17th century. So Newton discovered he formulated mathematically the gravity or mechanics with the calculus. The first direct result of this is a steam engine. 1736, right? James Watt. I'm not sure about the year, but it's around that time. James Watts, right? So when after Newton formulated Newton's law, started the major industrial revolution. So industrial revolution, 산업혁명, is actually the result of a discovery of Newton's law and calculus by Newton. Because after Newton, they were able to analyze force mathematically. And if you can analyze, you can design. So analysis leads to the design of the machine. And that one thing led to another, it became an industrial revolution. Maxwell's equation, or the first thing, this curl E is minus partial T partial B. This Faraday's law led invention of generator. Electricity. So without electricity, we don't have a light, we don't have a projector, right? etc., etc. So this is another, maybe you can call it the second industrial revolution with the invention of electricity, 전기. The modern civilization is based on machine, but also another one is electricity, right? Actually Maxwell discovered that. Curl E minus T round B, curl H, partial D plus J. So Maxwell did try to use this. What happens if you take curl again? This is B or F. And we have some space. So let's continue this. Is equal to partial T, partial curl epsilon E what happens? Plus J. Sorry, maybe I should do this the other way around. It's the same, but bit more complicated, right? Curl T, J. It doesn't matter. Is equal to partial T and partial E, curl cross epsilon E plus curl cross J, and we need a more space here, so move this along here. Epsilon partial T partial curl E plus J, and this is actually minus partial T partial B, right? Which is same as minus nu partial T partial H. So we have equation, where is it? So gradient of divergence of H minus Laplacian H is equal to minus mu E partial square H plus cross J. So maybe I can borrow this space. So let's move this. Yeah. Can you follow me? So we have Laplacian H minus epsilon nu partial square partial H is equal to gradient over h minus. But this part, this is important part. So this is actually called wave equation. That means, so Maxwell discovered that the solution of the Maxwell's equation is actually wave. So electromagnetic field is a wave which is propagating solution. So 1908. Okay, I used to remember all the important date. I think it's 1894. 1894, Hertz. Actually proved that the electromagnetic wave can be generated and can be detected. And as a result, we have this wireless communication. So Newton actually first opened the door to the civilization by mathematically formulating the gravity or mechanics, and also invented the 미적분학 calculus. So that led to the invention of machines, industrial revolution. But about 200 years later, so Newton was 1650 or something, and Maxwell was about 200 years later, 1876 or something like that, around 200 years later. So it took us for another 200 years to understand the electricity and magnetism in terms of mathematics. And then after he did that, the Faraday followed the theory to invent a generator. And about maybe 30 years later, Hertz showed that the electromagnetic wave is actually a wave. So wave can be generated and detected. So Maxwell's equation is actually the forerunner of the IT revolution, we call it the modern technology we have. It's basically using wave and electricity, right? Computer, everything, depending on that. And third discovery is 1920s quantum mechanics, but that is still going on process. But we are now taking the benefit of those two great scientists, Isaac Newton and James Clerk Maxwell. And the reason why we are learning vector analysis, et cetera, is to understand mathematics, how mathematics is important. So, because tomorrow is the start of a holiday, maybe I can stop today. What do you think? Any questions? It's a bit of a math with a history today, but I hope that motivates you to study a bit harder why this is important.